Let's talk a little bit about the process of compiling code from Java into the format that the machine needs to actually execute and run that code. So let's think about talking to a computer. First off, we could try the Star Trek route and just say, for example, like our clip art friend here in the slide, computer, print hello world. And, you may have used Dragon Naturally Speaking or one of these other programs, but what you're going to get back is a big question mark from the computer, because computers don't speak English. They speak machine language. All right, so we've got to get this straight, that computers speak one language, humans speak another. We need a way to reconcile this difference. And remember that machine language, simplified, is the native language of a computer system. And machine language is usually tied to the system architecture. In fact, it's pretty much always tied to the system architecture. So Intel chips have one set of machine language. Okay, ARM processors, like are found in the iPhone and the Palm Pre and those types of smaller devices, have their own machine architecture. The PowerPC chips from IBM have their own. So there's this low-level machine language that the hardware expects to have the information presented in, so it understands what to do. So we could learn to speak that machine language, correct? We could learn to speak zeros and ones, and people actually do this. And if you ever go ahead and take an assembly language class, you'll get pretty close to speaking to a computer in zeros and ones. And there's a great history of the Apple I, built by Steve Wozniak, where he could actually program in low-level, technically in his case hexadecimal code, directly to the hardware, because he built it and he knew exactly how everything was architected, and he could speak to the machine in its own language. But this isn't really practical, I mean, we could speak to the machine like that and it would say hello world, but the amount of time it would take us to learn to speak machine language at the lowest level would be a bit ridiculous. And if you really think about it, humans speak better in words than they do in numbers. We want to speak or program in a high-level language, okay? And Java is a high-level language. It abstracts the complexity of the machine. I oftentimes simplify this too by just saying, like, okay, look, high-level languages are a little bit more like native human languages, and in our case, like English. So high-level language allows us to speak in a way that we're more comfortable with, and then we have to have a process to get that high-level language into a format that the computer is comfortable with. The ideal here would be that we would say, hey, look, computer, print hello world. And the computer would understand exactly what we're saying from our high-level language and produce the output hello world. How do we get from human-readable language to machine-readable language? We introduce a program called a compiler. And a compiler's job is to take one form of a language and convert it to another language. Okay, there's a really generic definition that we want to go here with a compiler. It converts one language to another. It's a program. If you're on Windows, it's a .exe file. It's going to actually convert high-level language into low-level machine language for us. And you might hear that a compiler converts high-level language to machine language, but again, stick with the generic definition. It converts one language to another, because there's cross-compilers that convert, say, Visual Basic version 6 into Visual Basic.NET, and there's also some other compilers that do things like reverse compile that'll take machine language and try to build it back into high-level human language. So the general idea here is it's a program that converts one language to another. In our case, we're dealing with Java. So we can say specifically that the Java compiler's job is to convert Java source code into what's called bytecode. So we have to talk a little bit about these terms, but we're taking human-readable Java and we want to convert it into something that the machine can execute. Now, there's this little bit of odd thing that I mentioned last week about Java, okay, and it deals with this process or this intermediate step of compilation called bytecode. The machine language of the Java virtual machine is called bytecode. And if you've pressed the plus sign in JGrasp, you've probably noticed that it generates what are called .class files, or not what are called, but what are .class files. They have the same name as your .java file, but they just have a new extension called .class. These are actually the compiled versions of the Java bytecode. Well, these are the actual compiled versions of the Java program that you have written. They are in the proper format to be run by the machine. Now here's what's different. Let's go back a little bit. If we look at this case, the question here needs to be, what language am I writing my computer print hello world statement in, and what type of compiler am I using? So for example, if I'm writing in a program language like C or C++, I would write my computer instructions in C. The compiler would then convert them directly to machine language for the operating system and target processor system that I'm on. It's pretty straightforward. Convert directly from programming language into machine language. That's how a directly compiled language works. Java is a little bit different. You're going to say, well, bytecode. You're saying bytecode, you're not saying true machine language. Why is that? What are these .class files? I mean, are these ready to be run on the computer? Well, let's talk a little bit about how Java actually works. Java is like a unique type of programming language in that it tries to abstract the hardware from you. I mean, think of the brain load necessary for a programmer who wants to program his application so that it runs on every computer in the world. Well, think of the limitless combinations of operating systems and processors, that are out there. I mean, there's many, many, many of them. If you go to Wikipedia or Google and you just look at, Google CPU or Google, operating systems, you notice that there's a limitless combination. Sun came up with this idea within Java of having a virtual machine. And virtual machines have been done in the past, but in our case, it's really like a simple computer that abstracts the entire computer system, and its job is to run bytecode. The JVM is like a tiny computer written in software that is guaranteed to be the same on every computer that you ever have it installed on. So think of that. Instead of having to worry about all of these multitudes of combinations of different hardware and operating systems, you can write to one computer. You're guaranteed that the Java virtual machine should work the same on every computer that it's ever built for. So the Java virtual machine is our Java runtime environment. It abstracts the computer and executes bytecode. So let's talk about how this works. Okay, computer, print hello world. We write that in Java. We pass that source code to a compiler. Once the .class files are created, we've got bytecode. The bytecode files are then, when we're ready to run the program, passed to the Java virtual machine, which you can think of as a tiny little computer that's written in software that's guaranteed to be the same on every computer. It abstracts or hides the complexities of the actual hardware. The JVM then takes the bytecode and converts the bytecode into native machine language for the system that you're on. What's awesome about this is you don't have to worry about the machine code of the native system. You just need to know how to write to one computer. In your world, your brain is happy. You can go home, well, I was going to say you can go home at 5 o'clock because you don't have problems to deal with, but programmers always have problems to deal with. The power here is that you write the program to only one computer, the Java virtual machine, the Java runtime environment. Now, can there be different versions of the Java runtime environment? Sure, it gets updated like any other software program. But if we go back, we don't need to worry about that last component. This is all we need to worry about. The Java virtual machine at the end of this chain. Who deals with the final part? The computer and the machine language conversion from the Java virtual machine over to the native machine? Sun Microsystems. They're doing what I would consider the hard work, so you can just jump right in and write really cool applications and do fun stuff. And eventually at the end we get, hey, hello world. So look, the Java virtual machine is an interpreter. Its job is to execute a programming language. In Java, the Java virtual machine is an interpreter that executes bytecode. We pass bytecode to the interpreter. Could we pass Java source code directly to the virtual machine? I mean, could they have made that decision in the design process to actually just convert source code directly to machine language? Sure, and many languages that are interpreted like Python or Perl do just that. They'll take the source code directly. There might be an intermediate compilation step in there that happens actually at runtime, but they do that. Now, in the case of Java, a lot of enterprise applications are going to be written, and a lot of people who want to deal with closed source applications where you cannot only the people inside the company are allowed to see the source code, and the bytecode gives them a little bit of security in that you're not just handing out your source code, which in some companies people feel that proprietary source code is a business advantage. I'm kind of an open source advocate. I don't agree with that, but the bytecode also gives you some level of protection for your intellectual property. Another term I don't like too much. So the idea of the Java virtual machine is that it's an interpreter. It takes the bytecode and converts it at runtime, at the time it's requested to be executed, into machine language. We could use probably an outdated term at this point, but worm to explain the Java programming environment. You basically write once and run many. What's really cool about this is if every Java virtual machine is guaranteed to be the same on every machine, you can write your program one time, and then you can put it up on your website or sell it, and it should run the same on a Windows machine or a Mac or on a Linux machine, or depending on if you appropriately program it to not consume tons of resources on a cell phone. I mean, the idea here is you can get a business advantage, and that's the thought behind programming languages like Java that utilize Java virtual machines, is that you write the program one time, and you write it to this Java virtual machine, and then that Java virtual machine, if it exists on a platform, like if there's a JVM for Solaris running on a Spark processor, which I'm sure there is, then it should run exactly the same as, running Windows on an Intel processor or running Linux on a PowerPC chip. Write your program one time, run it in many places. People say, Windows is the primary market share leader in most places, and it is, but you figure that's like 80-90% of the market. You're still 10% of the people out there that you want to target and get their money if you're writing an application. I mean, your store shouldn't turn away 10% of all people who want to come in and patronize your store. So same thing with your applications. You want to get out there as much as possible. So look, here's the takeaways for this lecture. You only need to learn to code for one computer, the Java virtual machine. The Java virtual machine is a piece of software written by Sun Microsystems. Its job is to take bytecode and convert it into a format that is understood by the underlying system. It converts it to the machine code and native system calls that the underlying system needs to get the job done. You don't have to worry about that. Life is good. Just like driving your car, you don't need to be a mechanic when you're a Java programmer. You only need to know how to work with the JVM. You do not need to know how to deal with the underlying computer systems of every computer out there. So look, Sun Microsystems really handles the hard work of abstracting the computer. I mean, for every operating system and every hardware architecture, they need to write a Java virtual machine. In the case of Apple's JVM, I believe Apple actually writes that themselves because you can license and build your own JVM. So now that things are growing towards the open source end with Java, I think you're going to see a lot more JVMs out there that are optimized and probably a little bit, maybe some more flexibility in that area. But anyway, the JVM handles the hard part. Okay, the side that faces you always looks the same. It's the exact same computer, but the side that faces the computer is always customized to work specifically with that system. And think about it. Sun needs to know how Windows, Mac OS 10, and Linux all work together with the systems that underlie it and different architectures. You don't. You just need to know Java. Very cool, right? A couple other things in terms of writing our programs to go over this process. We write Java source code. We click the plus button in JGrasp to compile it to bytecode. We then execute the bytecode, which is passed to the Java virtual machine to be executed. The Java virtual machine then converts the bytecode to machine-specific code so you don't have to. And I say usually here because there are ways to make specific calls. You can actually write Java programs that only run on Windows. But I would probably argue if you're going to do that, you shouldn't be using Java. Somebody could always disagree with me on that, but just something to think about. So the JVM converts the bytecode to machine-specific code, handles that really difficult part. And finally, if you think about it, right, you should only need to write a program once, and you can deliver it to multiple systems. That's pretty powerful from a business standpoint. It affects your return on investment. The only thing you need to do is just make sure your users have the correct Java virtual machine installed. So if you're writing to Java Virtual Machine 1.6, like we are in this class, make sure that they've got that version installed. And you need to just really make sure that that's taken care of. And most people, Java is pretty ubiquitous at this point, and most people, if you've got a Windows machine, you usually see that update, or if you have Java installed, it says, hey, there's a new version of Java out. And most systems will handle keeping around older JVMs, but you just have to work to make sure that within that minimal number of Java virtual machines that are available out there, that your target user base has exactly what they want installed. Just a quick comment, I wanted to give some credit to that nice Macintosh picture that I got off Flickr. It was available through a Creative Commons license, so it was available for nonprofit use, and I wanted to give a link to the original photographer to their website on Flickr. So that's the process of compiling. Hopefully this is helpful. If you have questions, post them to the discussion board, and we can discuss in more detail.